Hello all. We are learning the various library block of Simulink. In a Simulink, now we will learn about some continuous library blocks. So in continuous library block, we have various library blocks like derivative, integrator, transfer function, PID controller. These are few important library blocks we will study now. So we will study about first this transfer function. So transfer function block models a linear system by a transfer function. The function of the Laplace domain variable S, the block can model a single input, single output, SI, SO, and single input, multiple output systems. Okay, so transfer function is most used library block among the transfer function blocks. So this block is used to model a linear system by a transfer function of the Laplace domain variable x. The transfer function transfer the input function in a different form. Most of the time, the transfer function is used as a filter. Let us understand how the transfer function can be used in automotive applications. Suppose we are developing the system for the power window of a car. User requests to open or close the window, or maybe user gives a request to set a target position of the window. In that case, we cannot change the window position, okay, like suddenly in that way. So window movement should be done smoothly only. The transfer function is used to reach the target position effortlessly, to use the target position effortlessly. So how can we use the transfer function and all these things? I'll show you here. First, I'll take one transfer function in front of you, okay. PRANSF. Yeah. So here you can see this is a transfer function in front of you. Okay. I'm taking one step input. Okay. And connecting its input. I'm connecting one scope to see the output here. Okay. And again, I'm taking connecting this input to the scope to see the output of the both input and output. So here I have connected the transfer function with the scope only. So I already told you to smooth and effortlessly output we are using the transfer function. So step is having that sudden changes of the step, but transfer function, after using a transfer function, you can see this is my step output in yellow, okay, and second one is my smooth output after using a transfer function. So that's why we will use. Again, if we come here and we make this legend, so here you can see my yellow one is step and blue one is a transfer function output. Okay, so for that purpose, that smoothing the output or like effortlessly output, like target position, we can use effortlessly. We are using a transfer function like power window. If we want to sudden stop somewhere, so we can use a transfer function. This is a first order transfer function. This is a first order transfer function. So the step function is used to set a target position here. Okay, the transfer function block has dialog parameter setting numerator and denominator and coefficient. Okay, where that the user can provide a vector according to the transfer function. So if I'm opening this transfer function, you can see here the numerator, coefficient, and denominator, everything is written here. Here we have a numerator coefficient and here the denominator coefficient. From there we can set the transfer function. Suppose if I am changing this to again writing 1 here, okay, and apply. Now here you can see s plus 1 divided by s plus 1, both are cut and equal will become 1. But if I'm adding one more here in denominator, okay, now it become a s square plus s plus 1, s plus 1, and that way it will work. Okay, so numerator and denominator coefficient we can add here and it will work in that way. So if I try to do something else, like here also I'm writing 1, again one more 1. At my numerator coefficients are more as compared to denominator coefficient. What happened in that scenario? So the time domain realization of a given transfer function is not it is not possible. The given transfer function is a improper function. The order of the transfer function numerator must be less than or equal to the order of denominator. Always numerator must be less than or equal to the order of denominator. This thing is very important when we study about the transfer function. Okay, so if you want to see the same thing, I'll show you in that way as well. Okay, here I'll change this and insert here to kind bar. Okay, okay, I have to close this mechanism. Now apply and okay, and I'll take one more transfer function. This is normal. Okay, now delete this. Okay, and this as well. And we will check. Okay. So my first one is like s plus 1 and second one is 1 upon 2s plus 1. Here I increase the t. As a t increases, the response time is also increases. So this is my transfer function 1, transfer function 2. Outputs are here. This is my transfer function 1. This is my transfer function 2. Okay. Again, I'll make it for the better understanding in a view layout. I'll make a two graphs. Okay, so here you can see the which is my transfer function 1, this is my transfer function 1, and this is my transfer function 2, transfer function normal one. So has this is a value of t. If I increase this t, the response time is also increases. So you can see in this graph that first one I have increased the value of t, that is 2s. So here you can see the graph is too smooth, that response time is increased, and here it's and the t value is 1 only, so here it suddenly increase. So increasing the t, we can make the response time also increased. That response to that response, that time is also increased in a transfer function. Okay, so let's do this example what I'll be plan to take it here. So here you can see g of s is equal to s plus 3 upon s into s plus 2. This can be considered as s square plus 2s. Okay, s square plus 2s. Okay, so I'll take one transfer function inside of here. Okay, I'll do this thing. I'll make it this f plus 1, s plus 3 is. I give the space in numerator. Okay, and this is a s square plus 2. That means the equation is s squared plus 2s plus 0. In that way can I write? Okay, so here you can see numerator and denominator is you able to see here. So I have converted these equation into this transfer function. Are you able to see here? I think so. Okay, fine. Now I will connect the scope. Okay, I will connect the scope and I will connect a constant as an input here. Right. And I'll take one more input to this scope, the input as it is. Okay, so if I'm simulating this, you can see I'll get sudden response of time. You can see in view in legend, you can see this is my constant input one continuously, and this is my transfer function input that is suddenly increased. Okay, so this is a change. Okay, there is various way to implement the transfer function as well. Okay, so I'll show you. I'll take one more transfer function. Okay, here, and I'll make it that 1 comma here 3. Okay, and here I'll make it like 1 and 2. Apply and okay. So here you can see I will be using 1 plus s plus 3 upon s plus 2. And can I use here for integrator 1 by s? Yeah, I can use it here as well. This integrator to get this output same. Okay. So here I have used one same input and connecting this. I'll connect, we'll delete this first. I'll connect that both output to the transfer function. Now this 1 by s is multiplied with this. So it will become same s square plus 2s. So the output graph should be same transfer function 1 and transfer function 3. If you are not able to see, I'll make it in a 2. So you can see the both graphs are same. Okay, so I have shown you here how we can use the integrator as well and how we can use a transfer function as well. So transfer function is used for the smoothly output or like effortless output where we want in that way. Okay, so that's it all about the transfer function. We will study next topic in next session. Thank you.